All right, go for it.
So that's what's great with the ODPs. So for the first time, every time I've run Asterisks, it's always just been a couple pause and then 0 out of 10 or 10 out of 10. For this one, it did this weird thing where it would it ran the SS 6 times.
Mm-hmm.
It'd go 0 out of 10, 0 out of 10, 0 out of 10, 0 out of 10, 10 out of 10, 10 out of 10.
Mm-hmm.
And I didn't know what that meant.
So different assignments have different numbers of tests they run.
Okay.
Right, each test is usually worth 10 points. So that one has 6 different tests it runs.
Because so I thought it was just that, I thought that no matter how many tests it was running, we only saw one 0 to 10 or one 10
No,
out of 10.
it varies from assignment
Okay, so I
to
thought it was 10 out
assignment.
of 10, but in actuality I got them, whatever that would have been, so 1 out of 3 or whatever.
Yeah, yeah.
So, okay. Because I thought it was caught in a loop, and it was running
Nope.
the test multiple times.
No, it's supposed to do
Okay.
that. And I do that mainly if there's some things that I think people will generally get right, and some will get right, and some that are particularly tricky, right? I put them in separate tests.
Okay.
So that, if you're missing one, you'll get 50 out of 60.
So from now on, if that happens, it just means I got however many of those tests correct, not the entire thing correct.
Right,
Okay.
right.
The ODPs work the same amount of times despite the number of tests they run?
I think they all come down to 100%, so yeah, they're all worth the same. And I usually try to upload those a few days after. I wait till there's a few of them, and then I go ahead and upload. We're done with ODPs for the rest of the week, so
Oh, cool.
nothing new until next week.
The programs on Friday.
Yeah, and programs due Friday, so concentrate on that. Say again?
Kind of behind on that.
Oh, okay, on the
So
program?
that's what I've been hoping. I'm like, man, I hope there's no ODPs for this.
Oh, okay.
So,
Well, the ODP should be possibly useful for the program.
well, that's kind of it
Yeah.
too now. Like after the last few ones, I'm like, okay, that'll make it not. So I'll
Yeah,
be
yeah.
up to date
So it
Thursday.
turns out
Right.
a very cool math teacher just taught us a different class. We caused me a heart attack. We're just thinking.
I think too, they're starting to make sense. Just like the last few ODPs have taken me a few hours, and then get the last one done in like 20 minutes.
Oh, good,
So
good.
it's feeling
Okay.
Yeah.
Yeah,
And
so
then email you.
that should be the experience, is that at some point, right, these things are going to look pretty straightforward, but the first few, right, if you haven't written code that uses scanf, right, that's where you figure it out, and that can take hours easily, right, because there's just lots of details there. So yeah, hopefully the time for those is coming down, and then at some point it's going to be a few minutes for each one, just kind of a pulse check. All right, so other questions?
I have a question.
Mhm.
Is it common when you're decrementing by one? I run into this several times. I'll have something like index, when index is not equal to 0,
Mhm.
do this, and you're decrementing by 1 every single time. But a lot of the times that doesn't work, and it wants it as when index is greater than or equal to 1, do this.
Not equal to 0 should, as long as you're starting positive and subtracting 1, it should get you the same place.
I was just wondering because I run into it like 3 times.
Yeah, show me that next time it happens, because I'd like to see it. But here's something that can happen. So you could find something like this. So let's write C code. Well, let's just write C code. So here's a basic while loop. I'll initialize x to 10 as a double, and while x is not 0, I'll print out the value of x and subtract 0.1. So about how many times is this going to run? About 100, right? It's going to bring down 0.1, and I don't know if it'll stop at 0 or 0.1, but it should be pretty close to 100. And that's a lot more than 100.
Do you not need to declare the return value?
It'll assume it's an int. It just gives a warning. So why is this thing looping more than 100 times? I never know how to output floats. There we go. So let's pipe this into more so we can actually see what it's outputting. So that all looks good. That looks good. That looks good. Got down to 0 and it just kept going. That's not a problem. This is really annoying. The first time you encounter this. At least the first time I encountered it, it drove me crazy for a while. Let's see if we can sneak up on this. Let's print out a bigger version of X. Nope, I'm not going to find it like that. So here's the thing. How many people have taken Engineering 270? Remember floating point format?
Yep.
Do you remember possibly, if you took it with me, converting the number 0.1 into floating point? And it's a bit pattern that starts repeating at some point, but it goes on forever. It's like in decimal when we write 1/3 as 0.33333, and we have to keep going. Well, in 64-bit floating point, we can only put in a certain number of bits, 50-some bits, and it's not enough to exactly represent 0.1. We actually store something close to that, but not exact. And so when we subtract 0.1 from 10, we don't get exactly 9.9. And when we subtract again, we don't get exactly 9.8. And when we get down to 0, it's not exactly 0. So floating point is a tricky thing where it would make a difference what you're describing, right? If you said if it's, so we could fix it like this. Well, X is greater than 0. Right. But we said X is greater than 0, and it printed out 0, and that tells us there's a problem right there. Because 0 should not be greater than 0. Well, evidently this last value of X it printed wasn't actually 0. It was a very small positive number. All right, so that's another hint. So floating point, be careful with. Be wary of. But you were doing integers, so yeah, let me know when it happens again. This is a problem in finance. If you're taking 10 cents off someone's account, you don't end up with exactly what you think. So you got the office space rounding problem. Yeah, exactly. All right, any other questions, comments? All right, I want to look at some bash stuff. So I want to look at quotation marks, and we're going to look at a different kind of quotation mark, a new kind. But let's review double quotes and single quotes and no quotes. So if I say echo, don't leave the house, that's not going to work. It's giving me this weird prompt, which is the prompt it uses when it's waiting for more input before it does what you're asking it to do. And the problem is I put a single quote in here, and it thinks I was starting a string enclosed in single quotes. So I can say what? And eventually, if I type in a single quote, it'll go ahead and say, okay, now you're done typing input, I'll go ahead and execute your echo command. And it didn't show me the single quotes because it assumed I was using that to group a string, right? Just like if I say echo quote, haha, right, it just shows me haha. That backslash thing that I keep doing by mistake, that's a way to continue a command onto a second line. So this is a test, and it pretends that was all typed on one line. But in a shell script, if you have a really long line, you want to break it onto multiple lines, you can use that backslash at the end to split it up. All right, so x equals hello. If I echo $x, it shows me the value of x. If I echo double quote $x, it shows me the value of x. So you can say things like double quote x equals $x, and it says x equals hello. Single quotes don't do this. Single quotes say $signs are just $signs. So if you want to print a $sign, an easy way is just put your string inside single quotes. But if you also want to be able to expand a variable, then you've got to do something like this. Okay, we also talked about things like asterisks, wildcards. Did we talk about that? Okay. So if I say echo asterisk, it's not going to print out an asterisk. Because when I type a command in the shell and that command includes an asterisk, the shell says, oh, this is a wildcard. Let's find all the files that match this wildcard, which is basically any file in the current directory, and let's pretend that that's what the person typed instead of the asterisk. So it thinks I actually typed echo followed by this. Right? Why? Because that's the stuff in my current directory. So I say echo star, and it thinks I said echo loop, loop.c stick. And when it runs the echo command, it passes all those arguments to it. And if I say echo star.c, it says, oh, there's one file that matches that, that's loop.c, so it calls the echo command with loop.c. So any command, word count, which tells me how many lines are in a file, I can say word count star, and word count thinks that I called it with 3 arguments, loop, loop.c, and stick. And this is what word count does when you have multiple arguments. Now, if I put that asterisk inside double quotes, it's just an asterisk. So double quotes suppress evaluation of wildcards, but they don't suppress evaluation of $signs. Yeah?
So if you wanted to type the word don't with the apostrophe, would you just do 3 single quotes?
I think this would do it. Nope. This will do it. But I don't know why the 2 double quotes inside single quotes doesn't work. Quotes are weird. And there was a case where a friend and I were trying to figure out something like this. We ended up getting to 10 consecutive quotation marks before it worked. Right? And I tried to tell him, I think you got to do 10 of these. And he thought I was making it up, so we tried 2 and 4 and 6 and 8, and all of a sudden at 10 it worked. Quotes are weird. And it's easiest if you can put the whole thing inside double quotes. But there's times when that's not enough. All right, and single quotes will definitely suppress things like asterisks. And remember, our 2 main wildcards are asterisk and question mark. Question mark matches 1 character, asterisk matches any number of characters. So if I say ls, l star, it shows me every file that starts with an L. And if I say echo l star, right, it just echoes the names of those files. All right, so there's a 3rd kind of quotation mark, which is a back quote. And on my keyboard, it's in the upper left on the same key as the tilde. It's not one we use very often, but it has a really, really powerful application in shells like bash. So here's a command date. Okay, when I type date and I hit enter, it runs a program which figures out the current date and time and prints it out. All right, and if I say x equals date and I echo $x, what am I going to see? DATE. All right, because I said x is equal to DATE. But it would be really cool if we could actually somehow set x equal to all of this stuff. Right? If we could actually execute the date command and have x set equal to the output of that. And that's what backquotes will do for you. So check this out. X equals backquote date, echo $x, there's the date. And the action is when I execute this command, date gets run, and the shell gobbles up whatever output it generates, and then it sets x equal to that output. So x is not associated with the date command, it's simply associated with this set of output. So if I look at x again, it's exactly the same time and date. It's not rerunning the date command. Right? Date got executed up here, and the output got stored in x. So I can say x equals backquote ls, and now x is equal to this space-separated list of files. If I said x equal to backquote ls-l, it's this big long string with all of the output from ls-l.
Could that be thought of like a function call then?
Effectively, yeah. So inside bash, we can execute whatever commands we want, and we can capture the output and store it into some variable by using backquotes around the command. So there's loop, which runs and prints out 100 lines of numbers and then says goodbye. I can say big var equals backquote loop, and now if I echo the value of big var, it's all that output. So you can run commands, you can save the output in variables, and then you can start using those variables in if statements or echo statements or whatever else you want to do inside a shell script, for example. And you can use that to deal with the results of commands. I'm making up some fake data here. All right, so here's a synthetic file for the ODPs. It's got more stuff in it usually, but whenever you assess your code, it writes a line into a grades file, and it has your username, it has the date and time, and then how many points the assignment was worth and how many points you were awarded, and some other information as well. But here's a simplified version of it, right? And let me go ahead and I had one student, he'd always assess his program like 5 times because one time he forgot to assess it. And I was like, make sure you assess your program before you're done. And so forever after, I'd see like 5 entries for his name. like one right after another, because you really wanted to make sure that it got loaded into the system. So that can be user 3 here. All right, so let's look at some other Unix commands. So one useful command is grep, G-R-E-P. And grep is a search command. So suppose I want to know how many times user 2 tried to submit their assignment. I can say grep user2 grades.txt, and it will show me all the lines that contain the name user2 anywhere in them. Right, so it's a basic search function. And the syntax in general is grep, something that you're looking for, some pattern, and then a file. And this pattern can just be a set of characters, and if that set of characters occurs anywhere in the file, it will show you that line. But this pattern can actually be something called a regular expression. So that's the RE part of grep. And regular expressions we're going to talk about later. We'll spend a few days playing with them. But they're a really powerful language, basically, where you can describe things that you're looking for. For example, I could look for any line containing January 19th or January 20th, right? Or any other patterns like that. But simplest version of grep space thing you're searching for space file. And most Unix commands, if you don't specify a file, they read from standard in. So if I say grep haha, it's going to read from standard in and look for lines that contain haha. So I can say this is a test. There's no haha in there. Funny haha, that's a joke. Well, that contains haha, so it'll print out that line. And other things that don't have haha, it won't print out, and so on. And that's a standard Unix thing. Most things, if they'll take a file name and the file name's not given, it just reads from standard in. So here's cow say haha. And if I pipe that into grep haha, it'll just show me the one line in that output that contains the pattern. All right, so there's my grades file. Suppose I want to know how many people got 100 on their assignment. Right, I can say grep 100 grades.txt, and it shows me all of these users. And I can pipe that into word count, right, which tells me how many lines I have. And it tells me I've got 7 people who got 100. Well, I've only got 5 people in the course, user 1 through 5. But user 3 assessed their program multiple times, right? So I'm getting some bogus information there. So let me show you, yes?
What's the 21 and 112?
21 words, 112 characters. And I could do word count -L, and it'll just show me the number of lines. But I don't know that command, so I would actually do something like this. And awk, we're going to spend a few days talking about towards the end of the course. Awk is a way to basically take input and break it up by columns. So this is an awk program which basically says print the first column of the input. So the first column there contains 7. But we're going to spend a few days looking at awk. So if I grep 100 grades, I got multiple entries that are the same. So here's something I can do. I can take this and I can pipe it into sort. And now my list is alphabetized, which means that all the entries by user 3 come one right after another. And there's another command I can use which is called unique, UNIQ, which says as you go through the input, if this line is exactly the same as the previous line, don't output it. So it will only show unique lines that differ from the line right before them. So in this case, if I were to take this and pipe it through unique, user 1, well, this line is unique, and this line's different from the one above, and this line's different from the one above, but all of these lines are the same as the line before it, so those will all get suppressed. And then user 5 will come out, as a new line. So if I pipe this into unique, there's my list of unique users who got 100%. And I can pipe that into word count -L, and now I can see there's exactly 4 people who got 100%. And if I said perfect equal to back quote all of that stuff, and I echo the value of perfect, it's equal to 4. So now I can put this in a script, right? Have all of this stuff as one line of a bash script, and this line will set a variable equal to the number of people who have gotten 100%. And if I do a grep-v, that'll tell me people who have not gotten 100, right? And I can do the same kind of thing. So there's all these tools we can use to process text files, right? So grep is a basic search. Sort just sorts things. Unique finds unique lines. 2 other commands that are pretty useful, tail and head. So tail shows you the last few lines of a file, head shows you the first few lines. So I could say tail-1 grades.txt, and it just shows me the last line. If I say head-1 grades.txt, it shows me the first line. If I want the third line, I could say show me the first 3 lines, and show me the last line of that by piping it into tail-1. There's the third line of the file. So these are not things to memorize, right? This is just an illustration of if you have, you know, these 10 tools at your disposal, you can do a lot of things with them, right? Once you're in the mindset of sort of putting them together, taking the output of this and feeding it into the input of something else. And seriously, it's like, you know, a dozen basic commands you can put together in a lot of different ways, right? Now there's other ways I could print out the third line of my file, right? I can write a sed script, I can write an awk script, I can write a C program. There's lots of things I could do, right? But I figured this out once and used it again. I've used it enough times that it just kind of comes to mind for me when I want to, you know, look at the 5th line of a file or the 3rd line from the bottom of a file, things like that. And if you like puzzles, right, you'll love this stuff because it's like, you know, Can You Escape puzzle or any of those others. Put the stuff together. So that's there. That's fun to play with. And then back quotes again can sort of take the result of all of this and throw it into a variable. So there's a PS command, and I want to see all the processes that belong to Nick. I'll put this into grep Nick. And I want to know how many processes I have running associated with me. Looks like 76 processes. All right, makes sense? Like I say, the specifics aren't the story here, right? You'll learn different commands, you'll figure out ways to put them together that make sense. It's more just the illustration of there is a variety of ways we can put commands together and get them to work with one another. All right, so let's talk about files. So I've got 4 files sitting in my directory right here. I can say ls-l and I see the permissions, the owner, the time they were created, and stuff like that. So I want to talk about something called links. And a link is a way to create a second file that refers to a first file. So for example, maybe you're writing a game, and your game is going to have one file that has scores in it, right? But maybe you want other people to be able to have a copy of that file, but not actually make a physical copy of it. You want something in each person's directory that refers to that one file. And so we can create what's called a link, and there's two ways we can make links. The first one is ln space old file space new file. And this is pretty painless. All right, so here's my old file. So I'm going to say ln old file, and I'm just going to say new file. And when I look in my ls, my list of files, I've got something called new file. And if I cat new file, it's got the same stuff that was in my old file. So I can go into old file, and I can throw a bunch of extra lines in here. And now if I cat new file, it's got that extra stuff in there. So it's different from a copy. I didn't just copy the contents of old file into new file. I actually created new file to point to old file. So anything I do with old file is reflected in new file. And you know what? If I go into new file and I make some changes, and then I cat old file, it's got those changes. So it's kind of like we have two files, old file and new file, that are referring to the same actual single file. Does that seem like a good characterization? And this is exactly what's happening. So if I do an ls-i, it says show me this inode number, this internal ID that the system uses to identify a file. And old file and new file have the same ID number, the same inode number, 4197745. They are the same thing on the hard drive. So this is called a hard link, or sometimes just a link. And a hard link basically says you have two or more files referring to the same stuff on the hard drive. So I can make a newer file that's a link to the old file, right? And I could make a newest file which links to newer file. And since newer file is file 4197745, newest file should be exactly the same inode number. Right? And if I look, that's exactly what I see. I've got 4 files all pointing to the same thing. And there's really no notion of like which one is the real file. Right? We know that old file was the one we started with, but you know, these all have exactly the same creation time, date, inode number. They're pretty much indistinguishable to the system. And I can get rid of old file and new file. And I've still got newest and newer file. And those are still intact. So the rm command is a little different from what we thought. Rm does not delete a file. Rm removes one of these references to an inode. And if you delete the last reference, then it'll go ahead and actually remove that file from the hard drive, sort of. But if you have something that's still referring to that inode, it doesn't actually delete the file. So I have to delete both newer and newest before that file actually goes away. And here again, if I do a rename, and I'm just going to rename newer file to old file, the inode number doesn't change. right? It's not copying it and then deleting the old one. It's really just changing this thing over here, this file name, old file, newer file, that's referring to that particular inode number. But think of that inode number as some spot on your hard drive, right, where your data is actually stored. So the alternative to this is this is a hard link. The alternative to this is what we call a symbolic link. And so here we say ln, but we put in a -s switch, old, new. Okay, let me show you what can happen here. So I've got my hard link still. New is pointing to the same thing as old file. I can move new into a different directory. Right, so I'm sitting in my home directory here, and I can cat new, and it's still referring to the old file, which is in a different directory. Right, because it doesn't care what directory I'm in. New is file 4197745. That's all it's got to know. Doesn't matter that there's something in a different directory referring to that same inode. When I try to interact with new, the system's saying, okay, I'm going to interact with file 4197745. All right, a symbolic link is different. So here I've got a file new, and I can cat it out. But if I do an ls-l, new shows up in this funny notation. It says new arrow old file. And the first column of my ls-l is no longer dash, it's the letter L for link. And so anytime I use the file new, bash will say, oh, you really mean the file old file. And it'll pretend that I typed old file instead of new. And it's not based on inode numbers anymore. So for example, if I move new into my top level directory, right, it says, oh, when you say new, you mean old file. Well, if I try to cat new, it's going to say there's no such file because there's no old file in my current directory. But if I move new into 224, where I do have something called old file, now if I cat new, it cats old file. Now if I remove old file and I try to cat new, it says no such file or directory. The link is still there. New is still set up as a symbolic link to old file, but there doesn't happen to be an old file. So it's a different kind of link. It's a symbolic or a soft link.
So would it be like a pointer to a pointer?
It's a pointer to a file by name, whereas a hard link is pointing to an inode by number, basically. So mostly we use symbolic links. Hard links are kind of out of favor, and it usually works pretty well. So it's kind of like a shortcut in Windows, right? So loop.c is file number 4197751. And if I remove loop.c and I do my ls-l, I don't see it anymore. So what happens when you delete a file? When you say rm and there's nothing else referring to it, there's no links, you just say remove a file. And then when I say ls, the file's not there anymore. What else happens? How do files actually get deleted? Do you ever wonder about this? they go into some kind of little disk shredder that like cuts them up into little pieces and throws them away?
The pointer to their location gets deleted.
The pointer to their location gets deleted. Anything else?
They just stay there until they get over
They pretty much stay there, right? The contents of that file that I just deleted are still on my hard drive, right? All it's done is it's said this file name, loop.c, no longer points to anything. So when I do an ls, I don't see loop.c anymore. And internally, the storage on the disk that was being used to store loop.c has been marked as available. Previously, there were data structures that said, okay, these parts of the hard drive are in use. These belong to a file called loop.c. That association has been taken away now. And if something needs to find space on the disk, it might use that space where loop.c was stored. But chances are the data that was in that file is still sitting on the disk in exactly the same place it was. So knowing that loop.c was inode 4197751, if I don't write anything to the disk for a while, I can probably go back into my disk and I can find those contents. So this is how undelete programs typically work. And worst case, you lose a bunch of information, you had a bunch of pictures. There's things in, say, a JPEG file that tell you it's a JPEG. Just like when you look at an executable file, you always see this ELF sitting at the 3rd, 4th, and 5th characters, right? Well, JPEGs have things in them that tell you it's a JPEG file. And you can just basically go through your disk and just start looking at the individual places on your disk for these tags that tell you this was a JPEG file. And you can reverse engineer the structure of the file and basically recover lost images that way, right? Until something else overwrites those locations on the disk. So a shredder, right, if you download a package for doing secure deletion, instead of saying RM, you might say shred file. And before it actually does the remove, it will overwrite the contents of the file. So that after you remove the reference to it, what's left on the disk is not the original file, but it's just some random pattern, right? So that's a more secure way to delete things, but it's not really secure. Because hard drives are a physical entity, and what's the technology that we use in hard drives? How are things stored? How's the coding done? Say again?
Transistors?
Not necessarily.
Like a hard disk drive?
Yeah, so what magnetism, that's what I'm looking for. Hard drives are stored by using magnetism, right? There's a platter covered with some ferrous material, and if it's a terabyte hard drive, there's 1 trillion times 8 with some extra locations on that where you can store ones or zeros, right? And you store a 1 by making a little dipole where north is up here and south is here, and you store a 0 by putting north on the bottom and south on the top. You got 8 trillion of those on your little 1 terabyte hard drive. And when you write something different into a disk, right, you may flip some of those. So if I wanted to write a bunch of zeros, it might go through and it might flip all of those dipoles. So let's say north is at the top, right? But if originally north was at the top, because I had a 0 written there, and now I write a 0, nothing really changes, okay? Except that this becomes a little more north, a little more south. But if originally I had north at the bottom, and now I try to write a 0 to put north at the top, the orientation of that is not quite as strong as if I had started with a 0. In other words, I can look at the current orientation of these dipoles, and I can say, this was probably a 1 before the last time you wrote it. Or this was probably a 0 before the last time you wrote it. So even though you've written new stuff into there, if you're good, you can go back and you can figure out probably what was written on there prior to the last write. So normally you have to do this multiple times, right? And make sure that you're flipping the bits back and forth. In the 90s, DoD had something called the Orange Book. It was their sort of standard for security, and it specified how many times you had to put in alternating patterns of 1s and 0s to do different levels of security when you were deleting things. Most people don't do this, right? You want to donate your computer to Goodwill, and you just, find the folders, hit the delete button, turn it off, drop it off. Don't do that, right? Chances are nobody's going to pull this thing out and do a forensic analysis on it. But if you've got financial information on there or things like that, right, you have to work fairly hard to actually make sure that stuff is not recoverable. And forensic experts or data recovery experts, right, are very skilled at being able to recover this information. You can also go into it with a microscope and do some analysis like that. I've never done this. So yeah, RM just removes references. Shreds will write patterns on top. All right, so tomorrow I want to start talking about GDB. So that's the debugging tool that we can use to help us trace execution of C code and see what's going on step by step. And that's going to be helpful for the rest of this course. It's going to be really helpful. It's going to be mandatory for 222, right? Because that's how we're going to figure out what our programs are doing when they're not doing what we want. So we'll start talking about GDB tomorrow.